Today we're going to be talking about surface integrals. Surface integrals and surface area have the same relationship as do line integrals and arcs. So those have like a similar relationship. So we're going to calculate a surface integral. The thing that makes it a little challenging is it requires creativity, and that we have to put the surface, which is written as f of x, y, z, we have to parameterize that surface in terms of two parameters, u and v. So when we talked about parameterizing surfaces, we did that in chapter 10.5. And so what we do is we parameterize the surface. We can really use any two parameters, whether it be r and theta, or theta and phi, or x and y, but we will need to parameterize the surface. And then the equation to do that is you take the cross product of the vectors that are generated by taking the partials with respect to u for x, y, z, and that's a vector r sub u, and then the partial with respect to v, the other parameter that you choose of x, y, z. You take the cross product, find the magnitude of that cross product, and that is going to be this part of the integrand. And then we multiply that times your surface where you have plugged in the parameterized variables for x, y, and z. So if you parameterize x, y, and z in terms of u and v, you can plug those in, and that's going to be your new integrand. And your bounds will be determined by how you will limit your parameters u and v to generate your surface. And so that will be your surface integral. One of the things a surface integral can calculate is if the integrand represents the density of the surface. So S is the surface, what you're integrating over. So if S is the surface, what you're integrating over, and f of x, y, z is a function that represents the density of that surface at any one point, then this surface integral can represent the mass of that surface. So that is one application of surface integrals. If you simply are asked to find surface area, this would be the formula. So it is the integral of 1 ds, the surface integral of 1 ds. In other words, it's the integral for which f of x, y, z is 1. And that just finds you the surface area. So let's do an example. And again, the trickiest part is really determining the parameterization, which is why we do 10.5, which is parametric surfaces, right before we do this lesson to kind of have it fresh in our heads. Okay, so we're going to do the surface integral over the surface S with an integrand of y, where the surface is defined as the portion of the cylinder, x squared plus y squared equals 3, that lies between z equals 0 and z equals 6. So we can first begin to picture what the surface is. We have a cylinder that goes from z equals 0 to z equals 6, and it is a repeated circle of radius square root 3. So we have x squared plus y squared equals 3, so that's that circle, and it gets repeated from z equals 0 to z equals 3. So from the xy plane through 6 units above the xy plane. So when you think about what your parameters should be, hopefully you're considering polar at this point, since we have a circle, and polar and circles go really well together. And with polar, normally we think of r cosine theta for x and r sine theta for y. However, does r change for this circle? No, it does not. So r doesn't need to be a parameter because we're just doing the surface. We're not filling in the inside. It's not a solid. So r is going to be radical 3. So we can define x as radical 3 cosine theta and y as radical 3 sine theta. And that gets us our circle with radius 3. And so we have to have theta vary to generate the circle, for us to go around the circle. But we also have to have z vary so that we can have it be a surface and not just a two-dimensional circle. So z has to vary between 0 and 6 in order to have it actually be a full surface and not just a circle. So we are going to have z vary by having z be a parameter. So we are going to have z be itself. And then what we can define is theta varying between 0 and 2 pi, and that will draw out the entire circle. And z will need to vary as well, so we can get the height on the cylinder. So that's generally where you start. You start with a picture, if that helps, and then you start with how you're going to parameterize. And notice how I'm kind of mixing and matching polar with, well, this would just be considered cylindrical coordinates, but I don't need to have r, theta, and z. I know r is fixed. The circle doesn't change its radius. It just stays at radical 3 because I'm not filling in the cylinder. I'm just looking at the edges. It's just a surface. It's not a solid. Any questions on this? So now I'm going to calculate my vectors, which end up being involved in my surface integral. So I need to find r sub theta and r sub z. Because remember, the cross product's magnitude is involved in that surface integral formula. So r sub theta is the vector that is represented by the partial integrals, or the partial derivatives, with respect to theta. So first we're going to take the partial derivative of x with respect to theta. So partial derivative of x with respect to theta is negative radical 3 sine theta. Then we do the partial derivative of y with respect to theta, radical 3 cosine theta. And then the partial derivative of z with respect to theta, which is 0. Then we're going to do the partials with respect to z of x, y, and z. So we're going to get 0, 0, 1. And so now involved in the surface integral formula, we have the cross product of these two vectors. So let's find the cross product of r sub theta cross r sub z. And the order doesn't really matter. We could do rz cross r theta because we're going to end up taking the magnitude. And the magnitude, the difference of the two vectors, if we switch the order, is they're going to be opposites. But the magnitude of two vectors that are opposites is the same. Just the direction will change, but it doesn't change the magnitude at all. So order here really is not going to matter. So I'm going to set up my cross product. So it's ijk, and then negative radical 3 sine theta, radical 3 cosine theta, and 0. And then 0, 0, 1. The zeros are always nice there. So what I get for my cross product is radical 3 cosine theta radical 3 sine theta, and then 0. And I get that for I by crossing out the row in the column that I is in. And you can see by doing the determinant, I get radical 3 cosine theta. And then just going across, doing that for J and K. Now, for my integrand, I need the magnitude of this cross product. So I'll take the magnitude . So from squaring each of the components here, I get 3 cosine squared theta plus 3 sine squared theta. We know that sine squared theta plus cosine squared theta is 1. So this is just square root 3. So now bringing it all together, all I need to do is say that the surface integral with respect to the surface S of y ds equals the double integral, and I'm going to put in the bounds now, 0 to 2 pi for our theta, 0 to 6 for our z. And now what I need to do is plug in y. Y is radical 3 sine theta, so I'll plug that in. And then I need to plug in the cross product of R for the magnitude of the cross product. Which is radical 3. And then I'll have my bounds or my variables of integration. So we'll have dz d theta. Then I'm probably just going to go ahead and split these up. Okay, so for our theta, I get negative cosine theta from 0 to 2 pi. And so for there, I get negative 1 plus 1. I get 0. Ooh. Times, and over here I get 18. Okay, so, not a super exciting answer, but you got the process. You parameterized, you found our theta and our z, took the cross product, got the magnitude, filled in the new version of the integrand, and then did the double integral. Any questions? Let's look at another one. Okay, we're going to need a little room for this one. So we're going to evaluate the surface integral of z with respect to the surface, so that's ds, where s is the upper half of a sphere of radius 2. So again, in my mind, one of the most challenging things is determining how to parameterize. Any thoughts for this one? How we would parameterize the surface, which is the upper half of the sphere?
Would we go with spherical coordinates?
Yeah, so spherical coordinates make a lot of sense, but we only have two parameters that we can use. Spherical has three, rho, theta, and phi. So which one can we not use? What one can we leave as not a parameter? Yeah, rho is 2. It's a sphere. We're not filling in the sphere, so rho is set at 2. So you might need to look back in chapter 9 to look at how the spherical coordinates are defined. I always have to look those up again, but we know that x is 2 sine phi cosine theta, and these are just from our spherical coordinates chapter. Y is 2 sine phi sine theta. Z is 2 cosine phi. Any ideas where and how we'll limit our theta and our phi to get the upper half of a sphere?
Theta 0 to 2 pi and phi 0 to pi over 2.
How'd you get that?
Well, for theta is the full sphere, so 0 to 2 pi.
Okay, so the cross section is a full circle.
And then since you only want the upper half of the sphere, you only go to the x-axis.
Yeah, so you go from the positive z plane all the way down to the xy plane, and that'll carve out the whole upper half. You don't want to go into the negatives for the z. You only want the positives. So you go from the positive z-axis down to the xy plane. So that's just 0 to pi halves. Good job. So those are our bounds. So now we have to find our theta, which are all the partials with respect to theta. Gotta love those zeros when they pop up. Then we'll do our R phi. Which are all our partials with respect to phi. All right, are we ready to do a super fun cross product? So please be careful with your thetas and your phis. I know you've been working with them in the past, but you mess up one and then it's all like yucky. So the way I've been dealing with, because you do so many cross products in this chapter or this particular section, is I just kind of lined them up like this and put the IJK on top to kind of picture, you know, kind of a shorthand cross product so I don't have to rewrite everything. That's what I've been doing. So it's up to you if you want to rewrite it as the matrix with the IJK or if you just want to do that. But I save a little room by doing it this way. So remember, when we cross product for I, we cross out the row and column that I is in, and then we do the cross multiplication, or we do the determinant in that mini matrix. All right, please let me know if you see any errors in this. So now we have the fun task of taking the magnitude of this. So I'm so excited. I'm going to change color to a fun color. Let's do a little magenta. Oh no, let's simplify it first. I'm going to simplify first. So the one thing we can simplify is the z component. What we can do with the z component is take out, oh, what can we take out? -4 sine phi cosine phi. And then what we have left is sine squared theta plus cosine squared theta. And so this is just for the z component here. So for that, because those are equivalent, we can just say that this is 1. So that's our z component. So that's a little nicer of a z component. So then all of our 3 components are now single term components, so you don't have to like have this multi-term monstrosity. All right, questions on that simplification? All right, now let's do it. Let's take the magnitude. All right, questions on my squaring and adding there? Okay, so what I noticed here is due to the sine squared plus cosine squared, this is just 16 sine to the 4th phi. And then I have that extra term on the end, so I'll just add that as plus 16 sine squared, gotta put sine squared phi, cosine squared phi. And then with that expression, I can take out a 16 sine squared phi. Equals square root 16 sine squared phi. Yep.
So you want just 4 sine phi.
Yeah. So this is something you have to keep in mind, that you might be doing this with spherical coordinates again. But you don't want to redo this process. So keep in mind, if the radius is 2, the cross product of r theta and r phi is 4 sine phi. So just don't do it again. What do you think it is if the radius is 1? Yeah, it's just sine phi, okay? And this is for a hemisphere. It doesn't even matter. We haven't even taken into account that it's a half of a sphere. We haven't even taken into account that it's the bounds. The only thing we've taken into account is that the radius is 2. What do you think would happen if the radius is 5? What do you think it would be? Yeah, so you only really have to do this once. So you might want to put a little star or highlight by it. So you can then say, okay, I got it. All right, so now we know the magnitude of the cross product of r theta and r phi. All we have to do now is the surface integral. So what I did in this step is I filled in z. This is z right there. And I filled in the magnitude of the cross product, which we found was r sine phi. I'm sorry, 4 sine phi. There that is. And I filled in the bounds of phi and of theta. Any questions on that part of it? Okay, can we split this into 2 single integrals, product of 2? Yeah, let's do that. So here we have a u du situation, a substitution. U is our sine, du is our cosine, phi, d phi. So the integral of 8u du, you can just do regular power rules for that. So we get 4 sine squared phi. You can see that the derivative of that would be 8 sine phi cosine phi. So if we substitute pi halves in for that, the sine of pi halves is 1. So we just get 4 minus 0, which is 4. And those are being multiplied, so that's our 8 pi. Questions? So again, the arduous process was all of the work with the spherical coordinates, but everything remains the same except for this, the radius of the sphere, and that we can just generalize. So it's not something we have to continue our work for. We can just move on knowing we've done the hard work, and the rest of it was pretty straightforward. Okay, so sometimes you might opt to stay in Cartesian form instead of parameterizing with different variables. It made sense in the prior two examples to go to spherical or cylindrical form because we had a circle being repeated along with z, we had a sphere, so that made sense. But what if it makes more sense to keep it in Cartesian form? Generally, what we end up doing is keeping x, so x just gets parameterized as itself, y gets parameterized as itself, and then you write z in terms of x and y. In that case, we can use this formulation, which is just a version of the formula we use for surface integrals. And so in your integrand, you just have to make sure that if you have z in your integrand, you're going to write z in terms of x and y. So your integrand will only have x and y's in it. And then instead of having to do the whole cross product situation, and the magnitude of the cross product, this partial z with respect to x squared plus partial z with respect to y squared plus 1 takes care of that for you. And so if it makes sense to keep it in Cartesian form, this is the formula for that. So we're going to try this out. So in this case, our surface is not a cylinder. It's not a sphere. And z is already written in terms of x and y. So as long as you can actually do the integral, it makes sense to keep everything in terms of Cartesian form. Also, look at their nice little bounds here. They're all numeric bounds in x and y. So yet another argument to keep it in Cartesian form. So for the formula, you do need to know the partial of z with respect to x, which is 1, partial of z with respect to y, which is 2y, and then the portion of the integral, which is the square root of partial z with respect to x squared, so that's 1 squared, plus partial z with respect to y squared, that's 2y squared, so that's 4y squared, and then plus 1. And that just really takes care of the whole cross product magnitude that we could do, but we don't have to do because the formula does it for us. So we get that the double integral, and we already know the bounds, so that's not going to be hard, is going to be y, because our integrand is y. Now, if our integrand had a z in it, we would have to replace z with x plus y squared, but we don't have to do that because our integrand just has a y in it. Remember, we have to have only x's and y's when we do our double integral. But it's y times the square root of 4y squared plus 2. And I'm just going to do dy dx. Our y going from 0 to 2, x going 0 to 1. I'm just going to go ahead and split these up just for clarity. 0 to 1 dx 0 to 2y squared, 4y squared plus 2 dy. Okay, so this one's 1. X from 0 to 1, that's just 1. This one I'm going to give myself some room over here. So it looks like this is like u to the half du situation. So I'm going to call this 8 because du is 8y, and then throw the 1/8 on the outside. So it's u to the 1/2 du. So what I get when I do that integrand is 1/8 of 4y squared plus 2. I have to bump up the power to 3/2 and then divide by 3/2, so that's multiplying by 2/3, and then evaluate that from 0 to 2. And so that's going to be 1/12 of 18 to the 3/2. 18 plugging in 2 for your top, minus 1/12 times 2 to the 3/2 power. And then just making that look a little better, 18 to the 3/2 is 3 radical 2 cubed over 12 minus 2 radical 2. So that's 52 radical 2 over 12. And then 13. Oh man. Any questions on that? So don't throw out the possibility that the parameters are x and y. So, we have kept z as a parameter and, done really a cylindrical parameterization. We've done a spherical, and there's times we have to get really creative and just do something we haven't even thought of before to make the integrals possible. Here is your assignment. It is a 2-day assignment because it's a challenging topic. It requires some creativity and some time. So I wanted to give you a little time in class to work.